Hello everyone, I'm Paul and today we're solving problem 3234. Count the number of substrings with dominant ones. Here it says this is medium, but this is actually very tricky, or at least it was for me. So next I will show you how to solve this visually and then we'll go with the code. We are given a binary string s and we need to return the number of substrings with dominant ones. Now we get dominant ones if the number of ones in the string is greater than or equal to the square of the number of zeros in the string. So the number of ones has to be greater or equal to the number of zeros. If we meet this requirement, we have dominant ones. Now, in case you don't know what a substring is, it's a contiguous selection of elements. So for example, this is a substring, this is a substring, this is a substring, but we can't form a substring with these two elements because they are not contiguous. For this particular example, we can take this substring and here we have 0 zeros and 1 1. And given that 1 is greater than 0 square, this is valid, so we can add 1 to the result. If we take this, we only have 1, so this is also valid. We add another substring to the result, this is 2. We can also take this, and here we have 1 0, and 2 ones is greater than 1 0 to the power of 2. And given that we meet this condition, we can add this to the result, so this is free. We can also take this substring, and here we only have a 1, so we add this to the result, and this is 4. Finally, we can take this substring, here we have 1 0 and 1 1. And given that 1 is equal to 1 square, this is a valid substring. We add this to the result. This is 5. And these are all the valid substrings with dominant ones, so we return 5. Now maybe you are thinking about trying every possible substring, and you can do this with a double nested for loop. The thing is that this requires big O of n squared and complexity, and here n can be up to 4 times 10 to the power of 4. And this is too much. We need to think about something more efficient. Now the main observation here is that if we count the zeros for every valid substring, we can have up to 200 zeros roughly. Why? Well, because if we do 200 squared, the result is 40,000, and this is roughly n. We can have up to 4 times 10 to the power of 4 characters. So if we consider only valid substrings, we can have up to 200 zeros, roughly. And what this means is that we can think in terms of big O of n times square root of n. This means that we are iterating every character in the string, and every time we are running a nested for loop to iterate only possible valid zeros. So first we are building an array to store the position of the last zero to the left of every index. First we are here and we don't have anything to the left of this number, so we put a -1 here. Next we are here, we have a 0. And we don't have any 0 to the left, so we put another -1. Now we are here and we have a 0 right here, so we put this index here. And this is index 1, so here we put 1. Now we are here and do the same. The index of the last 0 to the left of the current index is 1, so we put 1 here. Now we are here and the position of the last index to the left of the current index is also 1, so we put 1. Finally, we are here and the last 0 to the left of this index is right here, and this is index 4, so here we put a 4. Here we have the previous array, this is the original string. Up here we have the indices and we are iterating this from left to right. So first we are standing here at index 0, meaning we are here, and every time we want to consider a substring which has the current index as the right endpoint, and the left endpoint is either the start of the string or the previous 0. And how can we get this left endpoint? Well, that's why we have this array. We can go to previous at the current index, and this is the left bound. So how can we get the size of this substring? Well, we take the current index and subtract the left bound -1. And this is 1. And what this one represents is right now we are looking at a string of size 1. A substring, sorry. This is a substring of size 1. Now in this substring we have 0 zeros and 1 1. And how do we get the number of ones? Well, we can take the size of the substring, meaning 1, and subtract the amount of zeros, meaning 0. And this is 1. So the amount of ones is 1. And now, given that 1 is greater than 0 squared, given that the number of ones is greater or equal to the amount of zeros squared, we meet the condition to add this substring to the result. Now the next question is, how many substrings should we add to the result? And technically here we have space for only one substring, so this is very easy to answer. Here we can add only one substring, so we put 1 in the result. Now we are here and we have 1 0, so we can add 1 to the amount of zeros. And the question is, this is the right bound, but where is the left bound? Well, we take the current index and subtract previous at the current index. And 1 minus -1 is 2. Meaning we are looking at a substring of length 2. Meaning we are looking at this. We will use a shape pointer to keep track of previous zeros. You will see why in a few seconds, but right now Shay is here at index 1 and I is at index 1 also. So the current substring has a length of 2, and if we want to get the number of ones, we can take this length and subtract the amount of zeros, and this is 1. So we have 1 1 in this substring. And given that 1 is equal to the number of zeros squared, we are ready to add 1 or more substrings to the result. Now the question is how many? Now in terms of space, how many substrings could we add which have this length and the endpoint is here at index 1? Well, we could take this one and this one. We could take 2 in total. So in terms of space, we can take 2 substrings. Now in terms of the main condition, we have just enough ones to satisfy the amount of zeros squared. What this means is if we do ones minus zeros squared, we get 0. So we have a tie. We have just enough ones for this amount of zeros squared. What this means is we can only take these plus 1 substrings, meaning 1. So in terms of the main condition, we can take only 1 substring. And the minimum between these two values is 1. So this is the number of substrings that we take. This is what we add to the result. So this is now 2. And this makes sense because we could take 2 substrings, but we just can't take a substring with only 0, okay? Because we need to meet the main condition. And remember that we are running a nested for loop here. We are iterating every character and we are iterating previous zeros every time. So every time we update the shape pointer to previous at Shay. So now Shay is here at -1. And given that the shape pointer is now out of bounds, we can update the I pointer. So now the I pointer is here, and every time we move the I pointer, the shape pointer starts at the same index. So here we have both I and shape pointers at index 2. And we do the same as before. Here we don't have a 0, so the number of zeros is 0 initially. And now the question is, what's the length of the current string, of the current substring, which has the right endpoint at index 2? Well, we do 2 minus previous at Shay. And this is 1, so 2 minus 1 is 1. This substring has a length of 1. And this makes sense because remember that every time we are taking a range from the current index up to the closest 0 to the left or the start of the string. In this case, we have a 0 right here, so this substring has a length of 1. Now the next question is, how many ones do we have here? Well, we can take the length of the substring and subtract the number of zeros, and this is 1, so we have 1, 1. And given that 1 is greater than 0 squared, this is valid. And here we only have one character and it's a 1, so we can add 1 to the result. Now we move the shape pointer to previous at shape, meaning here. And here we have the same question, what's the length of the current substring which has this index at the right endpoint? So we do 2 minus previous at j, and 2 minus minus 1 is 3. So we are looking at this substring. Every time we move the shape pointer, we take a new 0 because these are indices for zeros that are to the left of the current index. So if we move the shape pointer to the left, every time we take another 0. Now, if this is the length of the current substring and we have 1 0, how many ones do we have? Well, we have 3 minus 1 ones. This is 2. And 2 is greater than 1 squared, so we are ready to add substrings to the result. Now, in terms of space, how many substrings can we add which have this index as the right endpoint? Well, we can add this one, and this one. We can add 3. And this number is given by this length. So, in terms of space, we could add up to 3 substrings. Now the thing is that we have already analyzed this substring and we don't want to repeat work, so we are just analyzing the 2 new substrings. Now the thing here is, how can we get the real number of possible substrings? Well, we can take the index corresponding to the shape pointer, 1, minus previous at j, and this is minus 1. So the result here is 2. This means we can take this substring and this substring. We can't take this one, okay? So now in terms of the main condition, here we have 2 ones and 1 0, and 1 to the power of 2 is 1, and we need to add 1 for a valid substring. And the result here is 2. And the minimum between 2 and 2 is 2, so we add 2 here and this is 5. And now we move the shape pointer again to previous at minus 1. And given that this is out of bounds, this is smaller than 0, we update the I pointer. Now the I pointer is here, and remember that every time we move the I pointer, the shape pointer starts at the same position. So right now we are at index 3. And we have the same question, what's the length of the current substring? This has index 3 as the right endpoint, and the question is, where is the left endpoint? For this we take the current index and subtract previous at j, meaning 1. This is 2, meaning this substring has a length of 2. And this makes sense because the closest 0 to the left of the current index is right here. So we take this substring. Now every time we reset the shape pointer and we update the I pointer, we are also resetting the number of zeros back to 0. Given that this is 1, this stays at 0. So if we have a length of 2 and we have 0 zeros, how many ones do we have? Well, we have 2 minus 0. Now 2 is greater than 0 squared, so this is valid. We can add substrings to the result. Now the question is, how many? Now in terms of space, we can have up to 2 substrings with this right endpoint. Now in terms of the main condition, we can do the number of ones minus the number of zeros squared plus 1 for the current valid substring, and this is 3. So we could have up to 3 valid substrings with 0 zeros and 2 ones. And the minimum between these two is 2, so we add this to the result. And this is 7. Now we move the shape pointer to previous at shape, meaning here. Given that we have just moved the shape pointer, the amount of zeros is 1. That's because of this 0. And we do the same as before. We are trying to get the length of the current substring. We take the current index and subtract previous at shape. And 3 minus minus 1 is 4. Meaning this has a length of 4. And this makes sense because we are going all the way to the start of the string. Now, if we have a length of 4 and we have 1 0, how many ones do we have? 4 minus 1, 3. These 3 ones, okay? Now, 3 is greater than 1 square, so we meet the condition and we can add substrings to the result. Now, in terms of space, maybe you are thinking about considering 4 substrings. This, and this. They all have an endpoint at index 3. Now, the problem is that we have already analyzed these 2 substrings. And actually, we have the result of this here in the result. So we should forget about this and focus on these new substrings. So in terms of space, what we need to do every time is to take the current position for the shape pointer, meaning 1, minus previous at shape, minus 1. And this is 2. Meaning we are considering these 2 substrings, meaning this substring and this substring, okay? These are the only new substrings at this point, so this is 2. Now in terms of the main condition, if we take the amount of ones and subtract the amount of zeros squared plus 1 for the current valid substring, the result here is 3. And the minimum between 3 and 2 is 2, so we add this to the result. So now we can update the shape pointer to previous at shape. Now shape is out of bounds and we can update I. So now we are here, and given that we have 1 0, we add 1 to the count of zeros, and the current substring has a length of 4 minus previous at shape, meaning 1, and this is 3. So this is the current substring. Now if we have a length of 3 and the amount of zeros is 1, this means that the amount of ones is 2. Here we have 2 ones. And given that the amount of ones is greater than the amount of zeros squared, this is a valid condition and we can add substrings to the result. Now the question is how many? In terms of space, we take the current index for the shape pointer, meaning 4, and subtract previous at shape, meaning 1. 4 minus 1 is 3. And in terms of the main condition, we take the amount of ones and subtract the amount of zeros squared and add 1 for the current valid substring, this is 2. And the minimum between 3 and 2 is 2, so we add 2 here, this is 11. So now the shape pointer is here at the index 1. And we take the current substring, meaning 4 minus previous at shape. 4 minus minus 1 is 5. So this has a length of 5. And given that we move the shape pointer, we add 1 to the amount of zeros. Now the amount of ones is given by the length of the substring minus the amount of zeros, meaning 3. And given that 3 is smaller than 2 to the power of 2, we can continue. Now the shape pointer is here out of bounds, so we update the I pointer. Now the I and shape pointers are here at index 5, so we take the size of the current substring, which is given by the current index minus previous at shape pointer, meaning 4. And this is 1. And this makes sense because right here we have a 0. So we have a substring of length 1. The amount of zeros is 0. This means that we have 1, 1. And 1 is greater than 0 squared, so we are ready to add substrings to the result. Now this has a length of 1 and we have a 1, so we can add 1 to the result. Now we update the shape pointer here, and every time we move the shape pointer we add 1, 0. That's because of this 0. We do the same. The length of the current substring is the current index 5 minus previous at shape, and 5 minus 1 is 4, meaning this has a length of 4. And this makes sense because here is the next 0. Now if the current length is 4 and we have 1, 0, this means that we have 3 ones. And 3 is greater than 1 square, so we are ready to add substrings here. Now in terms of space, we could add 4 because of the shape index, which is here. 4 minus previous at shape, and 4 minus 1 is 3. So we could add this, and these substrings. We can't add this one because we have already analyzed this and we already have the result in the result. Now in terms of the main condition, we do 3 ones minus the amount of zeros square plus 1 for the current valid substring, and this is 2 plus 1, 3. And the minimum between these two is 3, so this is now 15. Now we update the shape pointer, we add 1, 0, this is 2, and the current range goes from 5 to previous at shape, meaning minus 1, and this is 6, meaning we are taking every element here. And if we have 6 elements and 2 zeros, this means that we have 4 ones. Now 4 is equal to 2 squared, so we are ready to add substrings. Now in terms of space, how many substrings could we take here? Well, we have already analyzed most of this. So we need to take the current index for the shape pointer, 1, minus previous at shape, minus 1. And this is 2. So we can take this substring and this substring potentially. And in terms of the main condition, we have 4 ones, and if we subtract 2 square, meaning 4, and add 1 for at least one valid substring, this is 1. And the minimum between 1 and 2 is 1, so we add 1 to the result, this is 16. And this number makes sense because we could take 2 substrings potentially, but the smallest one has 2 zeros and 3 ones, and 2 squared is 4, and 4 is greater than 3, so this is not valid. The only valid substring in this case is this one, the largest one. Here we have 4 ones and 2 zeros. Okay, that's why this is 1, and given that this is smaller than 2, we add 1 to the result. Now we update the I pointer, reach the end, and return the result 16. As I told you before, time complexity for this will be big O of n times the square root of n, and space complexity big O of n. Remember that we need to build this array. So with this in mind, let's go with the code. First we say n is the length of the string, and we are building an array to store the position of the last 0 to the left of every index. This is an array with -1 times n. And just to be clear, previous I is the position of last 0 to the left of the current index. Okay, now we need to fill this array. So for I in range from 1 to n, if the previous character is I-1 is a 0, here we say previous I is the previous index. Else we say previous I is previous I-1. Okay, so now we say result is equal to 0, and for I in range n, the amount of zeros will be 1 if the current character is a 0, else it's 0. Now every time the shape pointer is equal to I, and while j is greater or equal to 0, remember that we are going in reverse here, and the amount of zeros square is smaller or equal to n, this is very important. Remember that we can have up to 200 zeros in total after we get all the valid substrings. Now we say the amount of ones is the current I minus previous j. This is the total range, and we subtract the amount of zeros. That's how we get the number of ones. Now, if the number of ones is greater or equal to zeros square, we are ready to add subarrays to the result. How many? Well, we take the minimum between the current and visited range, meaning j minus previous j, and the surplus of ones in the entire range. Remember the approach. This is given by ones minus zeros square plus 1. And just to be clear, here we take the minimum between the current and visited range and the surplus of ones in the entire range. Now, every time we update the j pointer to previous j, and we add 1 to the amount of zeros. Finally, we can return result. So this is the entire code. I think this is right. Now let's submit this and see if it works. As you can see, this works and it's very efficient. This was very tricky, to be honest, so if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.